everything we've done so far pretty much boils down to the fact that if you have a function f of xy, and let's say that's z equals f of xy, then if you have a point x naught, y naught, z naught is f of x naught, y naught. Tangent plane at x naught, y naught has the form z minus z naught equals this, fx times x minus x naught plus fy times y minus y naught. And the change in the value of the function f is fx evaluated at your point times delta x plus fy evaluated again at the point times delta y. And this approximation is good as long as delta x and delta y are small. So this is good for small delta x, delta y. This leads us to think about what would happen if we took the limit of this. Okay? So if we take the limit of the change of the delta f as delta x and delta y approach 0, what are we going to get? I don't want to go into too much detail on that, but the limit as our region shrinks of delta f we're going to call df, the differential. Now you remember differentials from first semester calculus. If your derivative is df dx, then df is going to equal your derivative times dx. I'm not going to write that down right now, but I'll probably write a note on that before we close out this clip. So in that sense, df tells you, if you know how much x changes, how much your function is going to change. For a function of two variables, x and y can both change, and then we're going to say that df is equal to your derivative times delta x, or your derivative times dx in this case. So far this looks like the differential for a function of a single variable, where instead of fx we might write this as f prime or df dx. Okay, the change in the function is equal to the derivative times the change in x. For a function of more variables, well, we're going to have to add fy dy. So if you have a change dx in your x coordinate, a change dy in your y coordinate, then the change df is going to equal this. And this is called the total differential. And it should be clear why this total differential is important and what it tells us about the behavior of the function. Now, just to mention the analogy with a function of a single variable, if you have y equals f of x, then if you have some point x naught, the function temporarily follows the tangent line, which has slope f prime, slope of a single variable. And if you have delta x, then the change delta f equals approximately f prime of x delta x. That's your change in the function value. And in the limit, we say the variable, well, f prime of x is df dx, which is f prime of x. And we can rearrange this symbolically by analogy with fractions to the form df equals f prime of x dx, so that if you replace dx by a small change delta x, you get an approximation to the small change in the function f. You might want to review that idea, but it's a fairly straightforward idea from first year calculus, and here we're just extending it without actually doing a detailed derivation at this point. The meaning of this should be pretty clear from what we've seen so far, and this should make good intuitive sense in terms of this.